Okay, good afternoon, everyone. Today, I and Manish are presenting a paper about improving transferability of adversarial examples with input diversity. We are going to talk, they introduce the paper, objectives of this paper, transformations used, related work, methodology, go through various experiments, 4 points, against points, and then we conclude all the findings. So convolutional neural networks are extremely vulnerable to small perturbations to the input images. So learning how to generate adversarial examples can help us to investigate the robustness of different models and understand the efficiency of current training algorithms. Here we introduce the black box setting where the attackers have no knowledge of the model structure and parameters. Most of the existing adversarial attacks only achieve low success rates. Single-step attacks perform better, and there is a poor transferability of adversarial examples because of the underfitting. In white box setting, attackers have perfect knowledge of model structure and parameters. So there is a comparatively better success rate of adversarial attacks. Iterative attacks perform better here, but there is a poor transferability of adversarial examples because of overfitting. So objectives of this paper: the authors aim to improve transferability of adversarial examples. They use the method of diverse input patterns. The authors apply random transformations to input images at each step. They test proposed input diversity on several networks under both white box and black box setting and single model and multi-model setting. The dataset they use to perform all experiments is ImageNet. Their attack method reached an average success rate of 72%, which outperforms the top one attack in the NIPS 2017 adversarial attack competition by 6.6%. And they have their code available on GitHub. Their work is inspired by the data augmentation strategy, which is the effective way to prevent networks from overfitting by applying a set of label-preserving transformations. So at each iteration, they apply random resizing and random padding to the input images with probability and maximize the loss function with respect to this transformed input. They also tried use other transformations like rotation, flipping, to create diverse input patterns, and they found random resizing and padding to be the best option to increase transferability. Let's go through related work. Dr. Zegedi proposed a box-constrained LBFGS method, but it's computationally expensive. Therefore, Dr. Goodfellow proposed the fast gradient sign method, which is less expensive due to a single gradient step. Dr. Kurakin extended the method above to an iterative version. Dr. Dong proposed a class of momentum-based iterative algorithms. And Dr. Lear proposed that transferability can also be improved by attacking an ensemble of networks simultaneously. Methodology. So let X be an image. Let Y true be the corresponding ground truth label. Let theta be network parameters. So the loss function is represented by the product of one hot encoding of the ground truth label and log of softmax of the logit's output. And our goal is to maximize the following loss function, where X plus R is the adversarial example. Now let's go through a family of GSM methods. The first method is the fast gradient sign method. The second method is the iterative version of fast gradient sign method. And the third one is the momentum-based iterative fast gradient sign method. Now we introduce the proposed methods of diverse input patterns. So the first method is diverse inputs iterative fast gradient sign method. And the only difference between DI squared FGSM and IFGSM is that they apply random transformation to the input with the probability P. The second method they propose is the momentum diverse inputs iterative fast gradient sign method, which is different from MIFGSM, is that they apply this transformation with the probability to the input. Now let's discuss relationships between all these methods. So if we set transformation probability to 0, then MI square FGSM degrades to MI FGSM. And if we set the transformation probability to 0, then DI square FGSM degrades to I FGSM. If we set momentum to 0, then MI square FGSM degrades to DI FGSM. And then here, if we set the momentum to 0, then MI FGSM degrades to I FGSM. And finally, if we set the iteration number to 1, then IFGSM degrades to FGSM. Now, let's go through attacking an ensemble of networks. Attacking an ensemble of multiple networks simultaneously can generate much stronger adversarial examples. The idea here is that if an adversarial image remains adversarial for multiple networks, then it is more likely to transfer to other networks. In this paper, the authors use the strategy where the logit activations are fused together to attack multiple networks simultaneously. The logits are fused by the linear product of ensemble weights and logit output of the kth model with parameters theta kth and here the ensemble weights. Okay, Manish.
Thank you. All right. Can you guys see my screen?
Yeah.
Okay, thank you. So thank you, Lina. So now that we know we have a good idea of what methodology the paper is following, let's try to look at the experiments they performed using the same methodology and what are the results that they got. So let's look at the setup first. All right. So the data set that you use is the ImageNet, and they chose 5,000 images, but they chose 5,000 images very strategically. So they inputted all their images and they saw what labels they are getting, and they used only the images that were correctly classified by all the models. So any image that was not correctly classified by any of the model was not used in the data set, because that doesn't make uh, very meaningful that is not very meaningful or experiments. So all these 5,000 images were correctly classified by all the models. Then they use 7 different networks. 4 of them were the normally trained networks, and 3 of them were adversarially trained networks. So they used a total of 7 networks for their experiments, and then they use a step size alpha of 1, and then the total number of iterations to be minimum of either max perturbation plus 4 or 1.25 times max perturbation. They set max perturbation to 15, and the reason behind setting it to 15 is that they want to generate humanly imperceptible examples. Setting it to 15 and does that job for us. But if we set to a higher value, then the images might not be humanly imperceptible. So they chose the value 15 because they want to generate images that are humanly imperceptible. Next thing, they set mu equal to 1, probability to 0.5, and then they applied random resizing to all the images and then paired them up to 330 by 330 by 3 in a random manner before they use those images as their inputs. So now let us look at how the attacking on a single network worked out for them. So in this case, we are going to look at a table. The structure of the table is in a way that, first of all, they are going to use all the 5 different attacks, and they are going to generate examples by using these attacks on these models. And then The images that you generate will be used to attack these models right here on the top, and they have mentioned the success rates in it. So in this case, the images has been generated from Inception version 3 by using these different attacks, and then those images have been used on these models, and we can see the success rate of attacking. So it is easy to see that DI square FGSM is performing way better than IFGSM in all the different cases. And then MDI square FGSM is performing better than MIFGSM in all the different cases. And we can see the similar results for the remaining tables as well. So this is Inception version 4. This is Inception ResNet version 2. So the images are generated by attacking these models. And then finally ResNet version 152. So these are the models. These all of 4 models are normally trained models, not the adversarially trained models. So all the images they have been generated by attacking these models. So just to give you a perspective of how good their method is performing, let's take a look at some couple of specific examples from this big chunk of table. So particularly this example. So if you want to see right over here, the images they generated were from Inception ResNet version 2, and they attacked Inception version 4 model using MIFGSM, and they generate a success rate of 45.9%. Consecutively, when they generated the same images and attacked Inception version 4 using MDI square FGSM, they got a success rate of 67.4%. Just to give you a perspective how good this is, so this is a 46.8% improvement as compared to MIFGSM, which is actually really good. And now let us look at attacking a model that was already adversarially trained. Now, because this model was actually robust, the percentages are low, but still, let's try to focus on how much they've improved. So let us take a look at this example. In the same case, when they attacked the Inception ResNet version 3, which was already enhanced and robust. So compared to MIFGSM, MDI square FGSM is performing like approximately 64% better, which is actually really good. Now, after looking at these, we can clearly say that combining input diversity and momentum improves the transferability of adversarial examples. But just in case we want to see how only the input diversity improves the success rate on our models, let's try to compare IFGSM and DI square FGSM, right? So in this case, the examples were generated from ResNet version 152 model, and then they attacked Inception version 3 model using IFGSM and DI square FGSM. And you can see that from 20.8%, they were able to take up the success rate to 53.8%, which is an improvement of 158%, which is actually really good. And then if we want to see the same thing for an adversarially trained model, we can always look at this example. So in this case, again, the images were generated from ResNet version 152, but the same attacking method, but this time they attacked Inception version 3 model, which was adversarially trained, right? And we can see that the attack percentages reached from 4.6% to 11.1%, which is again a 141% improvement, which is actually good. So these are the images that they have displayed. So the top line describes the clean images, and the bottom line describes the adversarially trained images. And it is pretty clear to see that if we shuffle these images up, it will be humanly imperceptible to tell which is a clean image or which is an adversarial image. And in this table, they're trying to say that their method is very robust, and it's not just limited to FGSM, but if you use any other attack method like CNW attack, it's still going to give you better results. So this table is about that. Now, first of all, let's try to trace back and think. When we tried to attack Inception ResNet version 2 model, which was enhanced, which was robust, we only reached a max success rate of 19%. Even though it's an improvement from what was previously proposed, it's still not that much. So now what they thought is, let's try attacking a group of networks simultaneously to improve the transferability. So that's what we mean when we talk about attacking an ensemble of networks. And in this case, they generate adversarial examples by attacking an ensemble of 6 networks, and they tested on assembled network in both the different setups, like in the white box setting and the black box setting. So in the table, wherever you see an assembled network, that means it's a white box setting. And if you see a holdout network, that basically means it's a black box setting. They have not used FGSM attack because it generated very low success rate on white box models itself. And all the assembled models were given equal weights and equal priorities. So all of the models, all the 6 networks are given equal model, equal priority. All right. So let's see how attacking ensemble of network turned out for them. So this is the white box setup, as you can see, assemble, and then they use these attacks to and and then they use these attacks and they found this result. So minus sign over here signifies that this is the particular model that was left out from all the remaining models. So uh, so we can pretty clearly see that their attacking strategy is not performing as well in case of white box setup as the previously proposed method. So if you compare DI square FGSM, it's generating lower success rates. In case of MDI square FGSM, it's again generating lower percentages than MI FGSM. So we can say in the case of white box setup, their model did not work as well as previously proposed method. Even though if it's marginal, it's not that much, but it's still a little bad as compared to the previously proposed methods. However, let's try to look at the black box setup. So in the in the case of black box setup, um, we can see all the percentages boosted for the success rates. So if we try to compare DI square FGSM with IFGSM, we can see that they did a lot better in every single scenario. And then if we try to compare MDI square FGSM, again, they performed really, really better than MIFGSM. And then we can look at some specific example like this one, where they just uh, left out inception version 3, which was robust and adversarially trained, and they almost quite doubled the success rate in case of MDI square FGSM as compared to MIFGSM. And one more example, you can see that the success rate of DI square FGSM is almost 4 times the IFGSM, which is actually really, really good. And now just to give you a perspective, with a single network attack, we were reaching a best percentage of only 19%. Right over here, we reached a best percentage of 39.4%, which is twice as much as we were getting with the single network attack, a little bit more than twice as much. So it is actually really good. Now, what they claim is that their white box success rates will improve if they move the transformation probability to a smaller value, or increase the total number of iterations, or use a smaller step size. So ablation studies is nothing but it's explaining how different parameters affect the success rates. So if we only consider it, so in this case, they have only considered an attacking an ensemble of networks, and they have tried to vary these parameters step by step, one by one, and see how the graphs are going to look like. The max participation is still set to 15, and for the same reason. So let's see how transformation probability is affected. So in this diagram, the solid lines represent the black box setup, and then the dotted lines represent the white box setup. And if you magnify this image, you can actually see that which line represent the adversarially trained models and which lines represent the normally trained models in each case. And it is pretty clear to see that In case of DI square FGSM, increasing the probability increases the success rate. But then in the case of white box setup, increasing the probability actually decreases the success rates. However, the decrease is not that steep, but increase is very steep. So overall, we can say increasing the probability increases the success rate in case of black box setup. However, in the case of white box setup, it reduces the success rate. And the similar trend can be observed for MDI square FGSM. The same thing, the solid lines represent black box setup, dotted lines represent white box setup, and the transformation probability is increasing when the success rate is increasing when the transformation probability is increasing, while the success rate is decreasing when the transformation probability is increasing in case of white box setup. All right, let's try to take a look at the how total number of iterations affect the success rates. Again, in the case of DI square FGSM, when solid lines represent the black box setup and dotted lines represent the white box setup, we are able to see the increase in the success rate with total number of iterations. However, if we switch to MDI square FGSM, in the case of adversarially trained models, the success rate is not affected. The adversarially trained models and black box setup, the success rates are not affected with the total number of iterations. However, in every other case, the success rates are always increasing. In the case of white box setup, in the case of black box setup that are not adversarially trained, the success rates are always increasing. Finally, let's try to take a look at how the step size is affecting. So the step size, we can see that is the, the smaller step size is actually better, and it stays the same way for a longer period of time unless you make the step size really, really big. In that case, it starts to decrease. But overall, step size is not affecting the success rate that much in case of DI square FGSM. And the similar trend can be observed in the case of MDI square FGSM. The bigger step size is usually decreasing the success rate of our models, of all the different models. Finally, let's try to take a look at their attacks and how they did against the top defense models in NIPS 2017 adversarial computation. So they tried to attack the top three defense models that were presented in NIPS 2017 and the three baseline models, and they tried to compute the average best on an average, which attack method is best. And here you see MIFGSM twice. The MIFGSM star are the results that were actually given out in NIPS 2017 competition. And this normal MIFGSM is the results that they got when they applied MIFGSM themselves on these models. The difference is because of random probabilities, but overall there's no difference otherwise. And in this, hello,
Yes.
um, all right, okay. I'm sorry. I thought my network broke down. So can you guys still see my screen?
Yeah, yeah.
Oh, sorry. Thank you. Okay. So about these, so TSALI is the top defense model that was presented in the NIPS 2017, and this model is actually based out on so denoising network for the defense mechanism, and Neil Thomas was the top third defense model that was presented in NIPS 27, and their model is based up on random transformations for defense. So the methodology is different, but you can still see that they are still achieving better success rates overall. So overall, as we discussed in the very beginning of our presentation, MDI square FGSM achieves 73% success rate, which is higher than higher than any other success rates. Elena, you want to take it from here?
Yes.
All right. So,
There are few for this paper points. So proposed methods improve the transferability of adversarial examples attacking a single network. DI square FGSM improves the success rates of IFGSM on black box models and maintains high success rates on white box models. Also, MDI square FGSM outperforms all attacks on all black box models and maintains high success rates on all white box models. Proposed methods improve the transferability of adversarial examples attacking an ensemble of networks as well. DI square FGSM improves the success rates of IFGSM on black box models and maintains high success rates on white box models. Also, MDI-FGSM outperforms all attacks on all black box models and maintains high success rates on all white box models. Also, their proposed method, MDI square FGSM, reached an average success rate of 73%, which outperforms top one attack at NIPS 2017 competition.
all right. So let's take a look at the engaged point for the paper. The first point and the biggest point here is that they use the same data set for everything, for all of their experimental procedures, which is image. It was interesting to see how their procedures are performing on different data sets. And then they have also said that their methodology is very versatile. However, I would have also liked to see their method performing better with some more different types of attacks. And I think the tabular data could have been represented better in subtables rather than representing data in such big chunks of tables. Also, they have said that their white box attacks can perform better than other attacks if they altered couple of parameters. But I would have actually liked to see that updating the parameters is actually doing the same thing that they have claimed. Also, the proposed solution is computationally very expensive and you need high-end hardware to perform these computations. And one point that is really interesting to me is that there is no data provided about how many networks are needed to generate what type of success rates. So they have assembled 6 networks, but what if I assemble 3 networks or 10 networks? Will my success rates improve if I use more networks, or if how the trend is going to be like? So there's no discussion for that particular point, which I would have liked to see. Finally, let's try to conclude the paper. The paper aims to improve the transferability of adversarial examples with input diversity. It applies random transformation to the input images at each iteration in the attack process. And compared with traditional iterative attacks, the results on ImageNet show that proposed attack method gets significantly higher rate for black box models and maintain the same success rate for white box models. Their enhanced attack reaches an average success rate of 73%, and the proposed attack strategy can serve as a benchmark for evaluating the robustness of networks to adversaries and the effectiveness of different defense methods in the future. And yes, finally, the code is publicly available at GitHub if you want to look at it. Thank you so much. Any questions?